Okay, good. We can begin. This is the schedule of the original class, which we don't have to be worried about too much. And I'm not used to virtual students, I must admit. I'm used to talking with people, so it is a bit strange. I hope you're still there. Yeah. So this is the summary of the lecture. First, we will go really briefly about some definitions, really high-level general concepts of what is machine learning, what is artificial intelligence, and then we will go into the section of cool examples. And then this is the easy and easily digestible part. Then we can get into the more complicated stuff where there are some details that maybe are too difficult. So just going really briefly about them. We will get about that later in the model part. Also, I wanted to say before starting, the idea of this course is maybe that there are some students that are in the process of selecting their master thesis. And this could be like a very easy introduction into, hey, this thing called machine learning exists. It's not that hard. It can do cool things. Maybe it could be a good topic for you as well as a master thesis proposal. I myself have also been studying a little bit of this in my bachelor, then long time not much, anything like this, and then selected it as a topic for my master thesis. So, and then studied from papers on my own. So it is possible to go into it, and it is quite.
Why do you say to study machine learning as your final thesis of your master?
I mean, it is totally voluntary to anyone to choose whatever they want, but it is an interesting area which can work. And it is the new, yeah. we can continue on this after the presentation, maybe. Yeah. Or at least after the first section, after the examples. Okay, getting into the presentation. What is AI, and then what is machine learning? So artificial intelligence, this is the only slide I'll be reading this much. Artificial intelligence is the ability of computers to perform tasks commonly associated with intelligent beings. That's like a Britannica, Encyclopedia Britannica definition. And this is also the only translation I have here because it's like a definition. So, briefly speaking, it is the idea of performing automated choices somehow intelligently. And machine learning is an example of artificial intelligence, and it is learning from patterns. So we have a lot of data, a lot of some measured signals or data or images or whatever, and some people labeled it. And we have a lot of data, maybe like millions of images, and millions of them are also labeled. This is the work-intensive part. This is the hard moment where someone needs to create this data set. That's not coming automatically. This is really sometimes this is the biggest block for a lot of projects to begin. There are no data annotated in this. We need to first start with that. So when we have this, the second part is, and there is a black box model. This is to be placed with some models from machine learning. When we have this, we can give it a new signal or new data or new image and then get an automatic decision. So that is, this is how machine learning works. We will get to this diagram again later when we get into the details of the models. So I'm talking about machine learning, and this definition was really high level and doesn't really mean anything. So we can go into the examples of some uses of machine learning, and there are 6 of them, starting from the first very traditional one, going into the more obscure ones that are nonetheless quite cool. So the first example is image classification. Probably this is where machine learning for a lot of areas started, with just large data set with images, and there are some models that can say, oh, hey, in this image there is a cat, in this image there is a dog, in this image there is a table, in this image there is a car. That's called classification of the image. And then there are some small other changes of these models, for example, localizing the objects within the image. So, okay, there is a cat and dog and duck, and they are here, 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 finding the bounding boxes. And even going further into the segmentation, meaning that finding the exact pixels and the exact boundary areas of the object. So here is like last year, roughly, a paper that has been produced in roughly last year. I hope you still can see this.
¿Pueden ver la pantalla?
Sí.
The YouTube as well.
Let's suppose that you're
Oh my
writing
God.
an important email to a colleague.
Whatever, God. I have a lot of videos here as well, so it will be a bit painful. Okay, so yeah, this is what the model can do. Finding objects in image, finding their areas, finding something like a percentage of how sure the model is. And you can imagine this is a task that is, for example, used in some autonomous cars. It can find the cars on the road, it can find the people on the road, it can find some object it has been trained on, but some objects it didn't recognize because maybe it was not trained on. For example, the buildings that are not really annotated because, yeah, those are not the items of interest. I don't know why umbrella is. Well, yeah, maybe umbrella is important as well. Paraguay. So yeah, this is kind of still quite traditional application of machine learning. Just object classification, localization, and segmentation. Fine, we get back and get into the more wild stuff. This is here, video captioning. So there is a man. So yeah, just look at the top left. There is a description that made by text, and this man is walking with his laptop, and there is a program running there with a machine learning model, which is on the spot annotating what is happening in like what is the notebook seeing. So we can see, okay, whoops, shit. Pardon my language. We can see what the model is seeing. A person walking down the street with a suitcase, fine. It's not correct all the time, but roughly it is getting like at least some idea what is happening in the image. The streets, lights, and also it's changing every second, so it's not hard to see. But there is a quite cool part here where the person approaches people and a man holding a hot dog. Okay, it's wrong sometimes. A man and woman eating a hot dog. A man. Okay, after a bit. Display case filled with lots of different types of food. So there is a model that has been trained enough so it can generate a sentence like this, which is it's quite cool. So the possible applications of this, kind of you can imagine for example, application for people who cannot see. There could be some model that's describing at least somewhat briefly what is happening. This could be when people who are blind can watch a movie in this way, in a sense. Or maybe it is actually not for anyone, but it is for some automatic analysis. YouTube has a lot of data. There are more videos that you can watch if you are watching it all the time, 24/7, being uploaded all the time. So it's quite hard to like get through this. If there is a model that can just go through all the data and like annotate all of it, fine, that's good. So that was an example of like using image and text together. Then we get into the area of style transfer. This is another application of machine learning, and now kind of touching more into the sphere of art, because it is possible to take a well-established painting style, something like Van Gogh's paintings or something, take the style out of it and then transplant it onto your own image. So kind of like, I don't know, paint it in that style. It's called style transfer, so transfer the style. And if you do it frame by frame, then yeah, you can do it in video. Oh god, this mouse. I have a mouse.
Yeah.
But there is no anyway. Okay. I mean, it's very sensitive.
It's sensible, I mean.
Yeah. So something like this is possible. You have a film, like already existing film, but you can colorize it in some, or like make it of style of your choice. Or here, Ice Age, as drawn by Van Gogh. Fine. So the usage of this can be in some video production. You can be stylizing the whole movie you have into some style that you choose. Also, this web page, you can try it later, whenever, if you're somewhere back home. You can upload your own photos and choose one of the styles, and it will change it into that style. So, yeah. I think there is a movie that has been made by Van Gogh himself that has been hand painted each frame by a different painter around the world in his style, and it was a really long process because every painter had to paint his own frame, and it really took a long time. And I'm thinking that this method actually that could be automated.
Yeah.
Maybe it would look worse, but maybe yeah. So this is some idea of usage of this. Okay, next we get into this example. Neural doodle. It is a neural network which is helping you paint in some sense. So you give it a really crude painting of, okay, category 1, category 2, category grass, and category sky, category river or whatever, category 3. And it is, when you run it, then it will kind of fill in the blanks of what you chose the area to be with what should be there from some large data set. So again, this was trained on some big data set of images, but now it is possible basically to help to co-create art with you, in a sense. Oh my God. So the final product is something like here. You have a quite nice image. Yeah, they have a final doodle comparison. So the idea of this, yeah, I don't know, it could be application for kids that they, I don't know, will draw something very easy and it will turn it into a painting. That's nice. Or if we step away from this kind of kid example or very like toy example into some more high-level idea, is that machine learning can be a tool that helps someone create art in a sense. So it is like a way of a helper for that co-creative processes, which is slightly similar to this example, which is SketchRNN. It is another example using totally different model, but basically what it does is it will figure out what you're trying to paint and then finish what you are painting. So we can have an example here with a model that has to load for some time. I use this, and I like the model called Spider, not Flamingo.
Let me see one. Slowly.
Yeah. So this is working in the browser. That's why it's taking some time actually, because it is just downloading the model or whatever into the browser, which is quite cool because in theory, in this thing, in the phone, you can have a machine learning model doing stuff.
No.
So now it is already trying to generate flamingos for me. So I will start, okay, with something, maybe a body, and it will co-create with me. Okay, it thinks it is a body, and look, okay, from a data set of some other people painting or drawing some things, it can co-create with me. Or finish, this looks like a dinosaur maybe, I don't know. Yeah. So yeah, going away from this one and continuing with the lecture. Again, this was a kid example, but like toy example, but this is something more scary. It is an example of generative adversarial networks. And generative models is a whole branch of models of machine learning. I'm thinking to dedicate one of the later classes totally on them because this is quite interesting. And these are not real people. This is a set of images that are generated, and these people don't exist. So some of them look quite nice. Some maybe look with some, like, there is something strange about the face, and they have cherry-picked the better examples to be front and the more obscure ones to be later. So for example, there is some face that, okay, this does not look correct. Like there are some faces that clearly don't work, but still, this is a model which can generate up to 1,000 by 1,000, so relatively high resolution images that look at least a little bit photorealistic. And this is quite new. This is 2017-18, and new kind of research is being done basically all the time in this sphere. And yeah, just the results are getting better and better. This is the process of training this model. So we don't need to get into the details what they exactly did, but yeah, it is slowly getting more realistic and more realistic. You can. It could be questionable. Some of the faces look strange, but still. Yeah. And more so, this is not done only on faces, but can be done on some other objects, such as, I don't know, I want to generate a plane, so it will generate me planes. I want to generate a room, it will generate me a room, and stuff like this. It is basically looking at already existing data set and trying to find, like, okay, these are the objects in the data set in this high-dimensional space. It can generate things in between those points in those high-dimensional spaces, which is quite cool. And kind of take two objects which exist in that space and kind of interpolate between them. So we can see what would be the mix of this space and this space and kind of have a interpolation between them. Okay, another example, cyclogen. This is, again, GAN, meaning generative adversarial network. However, in this case, it can do more crazy stuff, such as this. Basically, it all looks the same after some time, so you could say it's transferring the style, but this is the method is being different in this case, and also I think maybe more powerful because the data that you give it is there are less constrictions with it, so you can change the zebras into horses, you can change the horses into zebras, you can transfer the style of winterness of the, I don't know, the assembled winterness of images in your data set, take it from one image and then put it in a different image. So you can like change summer photos into winter photos and vice versa, and the results are quite realistic. Quite cool. Okay, and yeah, there are many more examples, and I think I would like to refer you to these two websites. Because there are some people who are actually artists with codes, basically taking these from like this background of computer sciences. We don't often talk about art, I think, in that, but maybe some people do. But I think in this moment it's getting kind of close to it. So these are two examples of quite interesting projects that they are doing. Yeah, just check this later when you have some time. The links will be in the presentation. And I think the advantage of this page as well is that he explains Gene Kogan explains everything that's happening in the and he has quite nice tutorials as well. So you can kind of make the same thing that he's creating. Okay, so.
¿Tienen alguna duda de todo lo que hay hasta este momento? ¿Preguntas?
No por acá.
Bien. There is no slide for questions. There are no supposed to be questions. Yeah. So this has just been some examples of the stuff that already exists. I think there will be more questions later, maybe. So now we get into the area of actually explaining a model, the machine learning models, and starting with neural networks. Actually, no, that's a lie. Starting with a very simple model that we can illustrate some concepts on, and then moving into the neural networks, which are a bit more complicated, but still, the ideas are the same. Okay, so I'm bringing back the idea of we have some black box, and we shove some data in it, and that some of it has been already labeled, and this is the one then this is the data set. And then we use it to generate some new responses, new automated decisions. In this case, machine learning models are often really data hungry, meaning that they need a lot of data. Which, thankfully, there are some big data sets. And one of them, maybe the most famous one, is ImageNet, which is a data set of images, 14 million images, that are all labeled by people on the internet who said, okay, this is a mushroom, okay, this is a dog, okay, this is a train. A lot of work has been done in this sense, and then a lot of work has been done to check that it's correct, at least to some degree. And on this data set, now we can use it to train some models. So this is, again and again, even up till now, we are working with models that maybe have been trained on this at initial level. So it is quite an important thing. And later in the presentation, we will also talk about it with some of the models. So yeah, this is a set of 1 million images used for the training. That's quite a lot. That's not something you can do with your camera on like a small, at the side of the class project. Like, it's a lot. Yeah. And yeah, how to now bring it into the model of, okay, we have some data, we have some labels, and there is some model. What are these things? So the data in this case are the images. We have 224 by 224 by 3 RGB channels image. That's a lot of data. And then we have a label mountain, and the same for like house, etc., etc. And then we come with something new, a new image, and we want to say, hey, model, this black box model, give us some classification. And this is just like, so you should remember, classification is the easiest out of all the tasks that we have been showing. So this is the easiest one. So what can be the black box model? There are a lot of choices. Some are more complicated, some are more suitable for some data, some are more like some are well known to be working with images and some with something else. So yeah, and we will start with something quite easy with linear classifier, and then go into the artificial neural networks, because this is the hype now, artificial neural networks.
You mean hype like that is the
This is what people are crazy about now.
yeah. That is what the most part of people are speaking at this moment.
Kind of, yeah.
It's a trending topic, you mean? Like.
Yeah, yeah. Okay, so now this is a moment to ask the students as well, even the virtual ones. This is a bunch of data that we have. Maybe these are like scores of some students, so maybe there is math score and stats score. So maybe this is a student who got 2 in here and 4 in here, and it is totally like a like random example. So like, okay, there are a bunch of students who are red in this class, and this class is possibly the students who didn't make it, whose score is quite low. And there are other points of students who maybe actually succeeded the class. This is just like whatever, an example. So we have this data, and we have 2 classes, fine, red and blue dots. We want to split this data somehow, or we want to figure out a model with this. What would be a possible way how to split it? A chance for the virtual students to respond.
¿Cómo se podría hacer una división de los diferentes puntos que tiene este
¿Cómo clasificar los grupos?
¿Cómo poder dividirlo? O sea, ¿cómo se le pone una clasificación? ¿Cómo lo digo?
To the coordinates.
Yeah, see?
You can take 2 different areas for every group, and any new point you can see in what classification for.
Yeah. And ¿qué podría ser una como visualización de esta segmentación del espacio? ¿Cómo podríamos hacerlo?
¿Cómo se podría hacer? O sea, está la segmentación y luego matemáticamente cómo lo puedes segmentar los puntos dentro de un plano. O sea, cómo puedes hacer la segmentación de los diferentes segmentos.
Esto es una palabra aquí, ¿no?
Esto es matemática básica, ¿no? Matemática básica.
Pues, so, switching back to Spanish, sorry, and English. So the kind of the most simple thing in this case is exactly what you said, splitting it into some two areas. And the basic splitting way is basically just a line. So you can like split it with a line, and that line becomes a model, and from this line you can classify. So for example, if you have a model, if you have a new point here, and we would like to say, is it the red class or is it blue class? Well, with this line, we would be giving stuff on this side of the line, this class. So yeah, blue, probably not red. What about this case? It's a bit tricky one.
Y por ejemplo, ese punto, que está, o sea, ¿a qué segmento corresponde?
No sabemos. The that, in truth, we don't really know because it's actually in the middle of these classes, so we don't know. But this is kind of like slowly getting us into the idea that we can have more lines that are splitting it, and we would like to know which of these line separators
¿Cuál es la mejor, cuál es de las dos líneas que están tiradas ahí, cuál es la mejor separación matemáticamente hablando para la clasificación? De una pregunta. ¿Cuál es la forma? ¿La izquierda o la derecha? ¿Qué opina el público del internet? Hablen.
Todos están muertos.
Están ahí conectados. Hablen. Hola.
Estamos acá, estamos pensando.
¿Cuál la puede jugar? Es mejor.
So, just the idea is that maybe like a point which is in here, which is kind of close to the blue ones, to be also blue. One point which is kind of maybe here, maybe it's still considered close to the red ones, so still we would like to have it red. So in this case, this model is working better because it's more balanced. There is maybe like we can call it like which one of them is good, better, best, is the one that has like the most splitting space in between, like this safe zone where we are kind of sure. So maybe actually this one on the right is the better one. Fine. So now we know which one is better, like which one of there is infinity of lines that you can put there probably. Which one of them is better? We know that now. I would like to kind of ask, what are the parameters of a line? What can we use to describe this line in a mathematical way?
Sí, dicen que cuando sabemos cuáles son las líneas para cuando sabemos cuál es el modo matemático para poder hacer la separación, pero ¿cuáles son los parámetros que deberíamos poder ingresar para poder decir si es que es azul o es rojo? Matemáticamente hablando.
Sí. Yeah.
Matemáticamente hablando.
¿Cómo definir la línea?
Sí.
Could be, yeah. And there is a parametric representation, which is like an equation basically with 2 points, or with some equation which looks like this. So we have some slope, that's this thing, and that bias which is pushing us up or down.
Es un X.
Maps, shit.
So, why is represented by 2 points? I mean, like, the mathematical function is receive 2 parameters. That's why. Yeah. Receive A and B.
Yeah. The 2 points, because you can calculate these 2 parameters of the 2 points. You can like find the line that is going through.
So, el resto a partir de 2 puntos sacar la inferencia, generar la ecuación general que te permite construir la recta en cualquier parte del plano.
Y esa es la fórmula X más B igual a 0. Y ahí reemplazo.
Cuando haces el cálculo de 2 puntos se genera la y el B.
So if we actually called before the line our model, then these are the parameters of the line, then these are the parameters of our model as well. So if we are training the model, meaning like trying to find the best separating line, we are actually training these 2 parameters. Training in this case is simply finding the best values for parameters for the A and B, and best in this case is the one that is splitting it with the largest split between. So this at some moment becomes an optimization task. You can say, okay, I want to maximize the whatever calculated distance, etc. And this is something that you can like send to a solver, and it will give you the parameters. So in this very simple model with just 1 line, we are parameterizing our model with 2 numbers. Okay. Yeah. So. In theory, this could be used with more classes. This is again like a toy. If we somehow could push all the images into 2D, fine, like 2 dimensions. There could be like an airplane classifier, deer classifier, car classifier, etc. We could have multiple classes. And also, there are some problems with this. So, well, this data is clearly separable with the line. There could be some data which is kind of overlapping. So finding the line is kind of more trickier because you have to account for some data not being on the right side. And there is some loss maybe you have. And some data is outright inseparable in this way. So there are some tricks that you can do with these models, but generally the idea is that we need to step away from just a simple line splitting model, especially if we are working with images which have 200, like let's say 200 by 200 pixels by 3. That's a lot of numbers. Those are those are the dimensions. So we have a really high dimensional item somewhere in this like not 3D but many D space, and we want to like find some separators in there. That can be done with simple line. Yeah. So now this is a space for questions.
Ahora, si tienen preguntas o alguna cosa que puedan colaborar o algún tipo de información, ahora es el momento. ¿Preguntas?
Estoy buscando
Mucha información.
¿Qué te lo digo? Por eso.
Con la línea.
The university from similar work with artificial neural network.
Yeah.
So I'll try to remember all the things.
Yeah.
¿Alguien más? ¿No tienen preguntas?
No, ninguna.
Okay, then so everyone gets that. Okay, in this case, the line was the model, and the line did have 2 parameters, and then training is just finding the best parameters. Okay, so now we are getting into getting near to the second part, which will be really hardcore, and there is a lot of stuff that I will be explaining. So before it, I will make a pause for like 10 minutes. And the second part, we will be basically stepping into a more complicated model, because we saw the line one. It works fine, but not with a lot of things. There are some problems with it. So we will be using some more complicated models. And more complicated in this sense means that it has a lot of more parameters to be set. And the ideas that we used before can be used here again. So if we have another model with another type of many parameters, the training is just finding the proper values for these parameters so they fit the data somehow. So they can separate the data well enough. So we will just be thinking about the different best scenario in the moment where they are just line. Okay, it's easy best, but in some other cases it's kind of more difficult to figure it out. And the parameters also, it will be less easy to imagine than just a line. But other than that, it's basically the same thing. So yeah. Good. I would like
Un pequeño break, ¿no?
Yeah.
O continuamos con la clase.
No, right. I need to read it out as well.
Demasiada información. Yo creo que
It's been like 30.
la mayoría de las personas que están viendo esto tuvieron las bases matemáticas. Las bases para poder ahora aplicar es otra cosa. Como que sí, como
I work with dataset, not images. So
What kind of data set?
Work with a classificator for the leaf, and work with different parameters of the leaf. And obviously, and final work, the neural network can be decided what leaf corresponds another dataset. But the level of work with images and work.
Images are a little bit special because there is something like there's something about images that you have some areas that are kind of close to each other. There are some they're correlated, the pixels which are nearby. But to some degree, it's just numbers as well. Like you can just say, okay, it's a lot of numbers in a square grid. So it is possible to convert this into like a vector and then use other models for it. With images.
Transmute to
or
image turn into a matrix.
Yeah.
Matrix.
Okay, although it's 45 now. At 50, we continue.
What kind of job are you doing at this moment in IE? IE.
One of the projects is this lecture, actually. Working on this lecture. Second project, I'm working with some photogrammetry methods, meaning from photos, converting many photos of some object into a 3D representation of that object.
Wow.
That's also not machine learning, but it's close.
It's not helping computer graphics, some kind of that.
Yeah. Actually, my educational background is computer graphics. So, yeah. But even from there, you can move quite easily into the machine learning areas. So, yeah. Okay,
Yeah, that is really, I really would like to understand, that all of this, but I think it's so much information when so much information is kind of, you need to read a lot, I think. On this.
You need to understand the basics, which hopefully will be here, and then you have to at least use it once, and then kind of it starts making little sense, little bit more, and like.
But tools
At some moments they start calling you, you're an expert in machine learning.
yeah, but tools are the same. I mean, like, if you choose a tool, for example, in Node.js or Python or Ruby or Java or whatever, that those tools will gonna work in the same way, with the same parameters, with the same algorithm, with the same classification method.
Python is used a lot with this, and to some degree you can just take a tutorial, follow it, and like it will probably work. And you don't really need to know the backgrounds of it. The moment that you need to know the theories is when it stops working for some reason. It's like, okay, what did I do wrong? And then maybe you realize, okay, it's actually this different type of data, and maybe for this I need to do something else. But for just to try something small, you can start with tutorials somewhere.
Because I don't know, first you need to have the data.
Yeah.
And after you have the data, you must.
But the data is provided by the supervisor sometimes. So that's the good part.
Where do you collect the data sets? Because the data sets is the most important thing here.
There are a lot of them online. So similar like ImageNet, there are other data sets, databases of other images or something like this. Or like for example Street View, Google Street View, you can, I don't know, write a code which will just download the images, every street, whatever, and you can create your own data set. Same way you can just like hack into the API of Google image search, not hack, but just like use them and just download a lot of images of like, okay, I search for cats, it will give me results and I will just download these. Fine, that's then like continue with this and that will bring your a data set. Maybe it will be messy at start, maybe you need to clean it, but this is one way. Or another way, you actually come into some project and they will have, I don't know, we have this program, we have a lot of data, but we don't know what to do with them. We need to classify them, do something. So yeah, that's another type.
You need to have the answer first, and after that, you need to have the problem that you will gonna solve. Yeah, because if not.
But there are a lot of problems and a lot of data as well. So actually, the hardest is sometimes to find something like innovative. So maybe sometimes with academic research, you need to like push the state of the art of machine learning a little bit, and it's hard because like where do I start to innovate something that's really difficult. So yeah. But a good topic, or good way how to do it is, for example, find a way where machine learning has not been used that much, but maybe they would still get quite like a lot of boost in the stuff that they are working with if you use those models.
Yeah.
So like interdisciplinary. Yeah. Hint.
Okay.
50. So yeah, we will start the next segment. Okay, so starting with neuron models. So before we were talking about lines, and the line was the model, and it had some parameters. Two in that case, very simple to find them, find the good values for them. And here we will have a neuron with many more parameters, and going forward, a neural network which will have many neurons, which will have many parameters. So a lot of parameters in total, and the training will still consist of just finding the best values for the parameters. So this way. So it splits the data the way we want. Yeah. What is a neuron? So we will be talking about artificial neurons, which are inspired by a biological unit in our brain, which is this image, this illustration. And this, what we can see here is, okay, an image of a neuron where it has some connections to some previous neurons somewhere in the brain. They are all coming into this soma, this place where all of these signals are somehow, something happens to them, they're aggregated, some maybe something happens to them, and they are sent out to the output side with some axon, some whatever. This image as well is this is a simplification that the biologists make. It's not like that. We don't really know what happens in our brain, the truth is. So I think there is a lot of research in that area as well. But still, we can use this as an inspiration for a artificial neuron, which is just a small model which is trying to mimic this, but it's not the same. And also, it's not the same what happens in here. So even if we have a neural network, it will not get intelligence automatically, sadly. So we have an artificial neuron which has some inputs again, these x1s to xn, it's these like n previous neurons that it's connected to, and at the other side it has an output neuron which is pumping the data to, or like sending the signals to. Something happens to the data here, so maybe some of the connections here are longer and it makes the signal a lot lower, and some of them are really close and strong, so it will make it fire stronger. So that is represented here by the weight. So we are multiplying x1 by weight 1, and it will give us, okay, maybe it will be close to 1, so it will keep the signal, or maybe it will be close to 0, so it will like lose the signal. And yeah, something happens here. There is a function which is collecting all of these, and that function is sigmoid, but we don't really need to go into that. And it sums over all the inputs and just aggregates them and sends them out into the output. And the output basically is something like a fire, don't fire. It is some number between 0 and 1, or depends on the model, but like, yeah, 0 and 1. So it's a real number, it can be anywhere in between. Okay, so when we were speaking about the line before, it had A and B. A was this, B was this. In this case, we also have a model which is taking some data in, popping out some data out, and the parameters in this case are the weights. For n inputs, we have n weights, each weighing a different input. So these are the parameters that we will be trying to tweak in a way that it corresponds to the data. Fine. Any questions?
¿Preguntas de algo de los sistemas neuronales?
I don't remember if you can change the sigma equation.
Yes.
For the activation.
You can have different functions.
But the classical is
the typical in the lectures, I think, is the sigmoid, because it's very easily like, okay, this is this line. The one that is being used right now is something called relu, which means there is 0, and then there is, I think, this, which means it's like a line, except for numbers that are under 0, it just lays it into zeros. So it's something like this, the output function. And it works for some reasons that are, yeah. Basically, a lot of this research has been done in the way that, oh, there is an idea, let's try it, and then if it works, good, let's continue with that. So no other questions about neurons?
¿Tienen alguna pregunta?
No, por acá nada.
Están todos digeriendo. ¿Sí?
Yeah, no? Okay. So yeah, let's continue.
Nada.
And let's continue with neural networks. So naturally, just one neuron wouldn't do it. We want to have something like a neural network of them. And the way they are put in this network is bilayer. So this circle is just the same model that we had before, and it is connected with all of these inputs 1 to n, fine, and then it has some output. This neuron is just another neuron, the same way, very simple, just connecting all of them with an output. This one, the same way. This neuron, the first one, has these weights, 3, or actually n. The second one has other n weights. The third one has other n weights, etc. And this is just the first layer. So let's add another layer, because now it becomes actually a proper network. And another layer, etc., all the way to the output. So here in this case, we have just one output, but in theory, there could be like a bunch of neurons as well outputting some data. So, and it is similarly just weighing whatever is coming to it and putting some output out. So this connection scheme is called fully connected neural network because each neuron is always connected with every input it can get, meaning,
the next slide.
yeah, meaning everything in the previous line. So fine, everything. Good. That's a neural network. And if we go into this schematic again, X are these inputs somewhere here, and Y are some of the labels out of here. So here will have the label, and here we will have the image. And then we give it a new data, and then we want to get a new classification. Just to bring it back into the stuff that we were talking about before. Fine. Training. So this is where the fun ends. This is where it becomes dramatically more complicated, and I will not go into the explanation of what exactly happens. I will very briefly talk about all of these points, but it's just to get an idea. It's not necessary to understand it right now. So we have a network which has a lot of parameters in each of its neurons, and yeah, that's it. That's the box, the black box. We feed data in it on one side, and we get the labels on the other side. And how to train this thing, how to set the weights, how to set the parameters is first we initialize it with something, maybe zeros, fine. And then we get all the data that we can, the inputs, propagate it through the network, meaning for each neuron, we will calculate whatever the output should be. For each next neuron, we will calculate whatever the output should be, etc., all the way to the end. Fine, this is pass in this way. We get the result, which is, it starts somehow wrong. So we get some like, the last neurons here will give us some output, which is what we are getting, some prediction. And we know it should be this thing, and it's somehow distant between each other. It's not the correct one. We get the error. We kind of get how far it is from each other. And we go backwards in the network. And we say, okay, for this neuron to be giving us something closer than this error, we need to change one of its parameters in this way. We do it, fine. We calculate the next layer before it, and do the same thing. And this is called backpropagation, meaning kind of propagating the error from the back all the way to the front. It is basically the same thing as optimization problem of okay, if we have an error, we can just set something. It's based on derivable equations that we can just go and fix the stuff that's coming in. And yeah, step 5, repeat. Basically, we do this again and again and again with new data, pass it, get the error, pass it back, try to repair the functions or like the parameters again and again and again, and with another epoch then, the same thing repeated a lot of times. We don't need to know this too much in detail. What we see later as like output of this algorithm or of this training method process is this kind of like something like this, where we have a loss. That's the error. Basically, loss is this distance, whatever we were getting like far away from each other. And it's going down. That's good. We are happy if it's going down. If not, it's something's wrong. But yeah, we are happy with loss going down, and the accuracy, which is how many times this whole thing, the whole model has been right, is going up. So it's getting near, maybe all the way to 100%. Yeah, that's it. Some questions?
¿Preguntas? ¿Se las ven orales? No?
Okay, good. Excellent. So let's get into the more heavy stuff, aka deep convolutional neural network architectures. Okay, fine. Architectures is easy. That's like just the way we put it together. But deep convolutional neural network. So we know neural networks right now, and there is something called deep convolutional adding to it, which we will explain now. These architectures are actually something that has been in work still from way back. There was a paper in 1998 presenting an architecture way how these neurons were connected, which was called LANET, and fine. And then in the year 2012, there was a boom with a neural network called AlexNet, which brings us back to the ImageNet dataset that we were talking before about. Around like 2010, I think, the ImageNet dataset has been released, and there was a competition started in. They published the dataset and said, okay, anyone who wants, they can just run their data on it, or like their models, and try to get the best results. So this is the moment where they started to use some of these convolutional neural networks. And okay, first 2 years they did not get it. This year, an AlexNet came. It's quite important model that we can see the error on this got really dramatically lower. And year after year, 2012, 2013, 14, again 14, 15, the error just lowered and lowered and lowered. And also what happened, the models got more and more complicated, more and more deep, and more, some tricks were used to train it and to get the errors down. So yeah, this is the case study. This is the model from 1998, and it looks dramatically complicated and scary because there are some things that we don't understand. But what we can get is that, okay, here is an input. In this case, it has been working with a handwritten dataset or dataset of handwritten numbers. So there is an input of 32 by 32 image. And all the way here, there are 10 classes, which will tell us it's 0, it's 1, it's 2, it's 3, all the way to 10. Fine. So that's what we get. There is an image on one side, and there is a label on the second side. If we jump into another case study, this is the AlexNet. Again, a scary painting with a lot of boxes, lots of numbers, and lots of connections that look very illegible. We again have an image on one side, 224 by 224 by 3, and on the other side we have 1,000 categories. This is actually the ImageNet, because ImageNet has 1,000 categories of items. Fine. This looks scary, these boxes, but all the thing that they are is just neurons connected in some way. So in order to understand it, we need to get deeper. We need to understand these new terms, what is deep and what is convolutional. Deep refers just to the fact that they just use more layers. So instead of using like 1, 2, 3, okay, this is a multi-layer perceptron, a model with neural networks, very simple, can fit any data. We just use a lot of them, a lot of the layers. And like it is going into, I don't know, some of the models from 2016 were using like 152 layers or something like this. Deep. Fine. The idea is that if we have more layers, we have more parameters in the model that can fit more data. But also it's harder to train, so yeah. And convolutional, that's the second trick that is being used. It is just referring to the way how the neurons are connected. Because if we remember last time when we were talking about the neural network, it is something like this. The neurons were always connected to everything that they could have been connected to in the previous layer. So this poor neuron is connected with this pixel, this pixel, this pixel, this pixel, this pixel, all the way to the whole image. And this is like a sample image. There could be 224 by 224 by 3, a lot of pixels, all of them connected with one neuron. So there are a lot of weights. And that was just for one neuron as well. If we have more, maybe like 128 neurons here, we have a lot of weights. This is unfeasible because you cannot train it. It's too much, basically. So the trick that has been used here is, instead of looking at the whole image, just looking at an area that's called convolution. An area, let's say 3 by 3, okay? And this is the only thing that the neuron is connected to. So it will have just these 9 weights because it's connected with this pixel, this pixel, this pixel, this pixel, this pixel, this pixel, but just these. It doesn't have connections with the others. And this area is being shoved around the image, basically calculating for each of the pixel, but the weights, the 9 numbers, are not changing. For one convolution, we just have 9 weights. It's as simple as that. So this is significantly less connections. Instead of the many thousands here, we have just 9, much nicer. So it makes the training much easier. And also it is using something like a property of images, which can be said, okay, if I have a pixel here and here, they are close to each other, they probably belong to the same item. If I have a pixel here and a pixel there, because I have a big photo, those two pixels don't correspond to each other at all. So why even connect them? Because like that would make no sense. So there is something called locality. So this small box that's moving around is basically picking up the things that are close to each other. Fine, convolutions are done. Another type of layer that we use is downscaling, which sounds maybe familiar because it is something quite familiar. If we use convolution, we get an image as a result. Basically, we run this square around and calculated the value on the way. We got the convolutional image, and then we downscale it. Downscaling is simply dividing the image by, like, downscaling it from 222 into 100, well, just half size. Fine, that's easy. This is again done so that we have less parameters to worry about later. We have half an image, it's a lot of less parameters, but also because then we follow this convolution downscale with another convolution and downscale. And the second convolution is again looking at like boxes of the image, and again calculating from this box with these 9 values, just 1 pixel, jump another pixel, jump another pixel, with all the time just with these 9 values. Nothing is too complicated to learn. And if we then look this convolution on this downscaled image, if we look at this area, what was it looking at in the original image? It is actually looking at much larger area. So this, because of the downscaling, was all the information here in this small area is roughly like this bigger box. So the fact that we continue with convolution downscaling and convolution downscaling and convolution downscaling means that the later convolutions, if you calculate it all the way back, they actually are looking at much larger area. So the first convolutions will be looking at 3 by 3. There is not much information you can get from 3 by 3. There is like maybe the edges. You can get like, okay, hey, there is this edge, there is this edge, there is this edge, fine. The later ones will actually have like a small, maybe pattern, maybe some small like, maybe something that is repeated in the dataset. And the later ones will have actually concepts, like whole objects in them. So if we are looking for cars, maybe whole wheel, some stuff like this. So how to see it in this early layer versus the later layers? It's something like this, where we have this is an example from a neural network, where this was the input, and these are like visualization of these convolutions. So while the ones in start of the model, they even couldn't get much like larger area. They were really looking at, I don't know what this is, maybe like 11 by 11 or something area. Only thing that they can get is just the like this feature that they can get is just the edge of some sort. This thing in the middle can start getting like some more like parts of the objects, fine, while the stuff in the back is looking at whole faces, basically whole concepts. So this could be a feature which is described. Okay, this is the mustache neuron, fine, good. This is another mustache neuron because there is some redundancy. This is the smiling neuron, fine. This is again the smiling neuron. There is the I don't know, this type of hair neuron and stuff like this. So in the later in the depth of the neural network, there is some feature that is representing some number that is representing how much is it close to these images, basically. Okay, depending on what you train, the neural network will train on different things. So while the first layers are usually just the same as well, because yeah, in all images that you can find, there are some edges. That's easy. But if we walk into, if we are working with faces, fine, it will be getting some parts of faces as the intermediate representation, and the ending representation maybe whole faces. Cars, the same, some parts are here, these are the final products. Here there is like a butt of an elephant here, butt of an elephant there, this is maybe an ear, something like this, parts of the elephant, how to assemble it, and these are like the bigger elephants. And this happens with the datasets. So it depends on what you are training. The model will actually focus on like it will learn what it has to look for. Yeah. So if we jump back into the case study that we started with, LeNet. This is the scary neural network from 1998. It's not as scary because, oops, shit, this keyword. Because what we have here is just the input, fine, a convolution, which is just, okay, it was looking at the area and it was giving the, like jumping with the block and giving, fine, that's easy. And there is a some sampling or downscaling, basically taking this image and making half of it, and then again another convolution, fine, and another subscaling, downscaling, fine, again half. And here we have these really tiny, now 5 by 5 images, fine. And what happens after? We actually want the model to be looking at all the data. We don't want it to like just focus on these boxes or something. It's fine that it does it. Up till here, up till this moment, we were happy that it's like just focusing on small regions. But at some moment, we want to take all of these like really high-level parameters that it took, these high-level features, and like, okay, connect all of them with whatever we want, because maybe all of those are important. So there is a fully connected layer, meaning this layer is just neuron which is connected with everything from the previous line. So there is a lot of connections going on in there. And this happens, okay, we have one fully connected layer, second fully connected layer, third fully connected layer, and the third one is made of 10 neurons. And each of these neurons, the way how we train it is that it represents 0 to 1 to 0, 1, 2, 3 to 10, the labels that we were training it for. Fine. If you look at the other example, that was also scary, we did have an image here, good. This was the representation of the convolutional layer, fine, 11 by 11 window, okay, it's just calculating the same thing. Then it takes this image, which is now 55 by 55, it makes an half of it, okay, this is downscaling, and then again, okay, this will be probably, I don't know, maybe also max pooling, so this is also downscaling in some sense. Here it's, I think this is convolution, and this is another convolution, and here, again, we have a block of fully connected layers. So when we know what these things are assembled of, it's not as scary, it's not as, like, you can get what's happening. The idea of convolution downscale, convolution downscale, convolution downscale until you are bored of it, and then after that, okay, you can connect it with a fully connected layer. So the idea is that at the start, this part is sometimes called fully connected, fully convolutional area or part of the neural network, because it's just fully convolutional. There are just convolutional neural networks and downscaling neural networks, fine. And it is basically getting whatever the image was and kind of bringing it into high-level features. That, okay, this is the elephant neuron, this is the car neuron, this is the, I don't know, pretty lady neuron, etc. And then we have a block which is taking it from this high-level representation into the classes. So this is the classifier. So we have like two blocks. One is the, we call it feature extractor, and the second one is the classifier, which is bringing them back into the classes. Questions?
Tengo una pregunta de la optimización de las imágenes que está hablando recién. No hablan.
Nada.
No, para ver, vamos.
Está súper complicado.
¿Complicado?
Es que es enredado.
Lo que pasa es que es demasiada información.
Sí.
Pero no sé si será tan complicado. Técnicamente. No sé.
After this, small visualization of this, like a small demo which can give some input into it, like how it exactly works. But still, if there are some questions now, si hay algunas preguntas ahora.
Vamos a hacer la demostración. El demo.
Okay. Bien?
Muy bien.
Okay. Good. So, so we have been talking about the convolutional neural networks, which have convolutional layers, downscaling layers, fully connected layers, and a lot of more tricks in the later papers that we will not touch at all because it's not that important. But these three are basically what makes a lot of the neural networks. And there is an interactive demo of this, of convolutional neural network, on a dataset called MNIST, which is a dataset of handwritten numbers. Basically, it is this. Because if you give this sort of image to the computer, how to translate this image into 3 as a label, as a int from this 32 by 32 image, it's also like, okay, this could be quite messed up too. Still, it should be able to recognize it. So there is this visualization. Okay. Whoops, I hope I don't kill it. Fine, good. So this will take some time to load, actually. Good. So this is the neural network architecture. This is what we saw before, which was the LANET. This is the simple one from 1998. There is the input image. All the way back here are the 0 to 10 labels. Good. And now we give it something. So we give it a slightly messed up 1. Okay. And here it is. So this is the input. This was the 32 by 32 image. And this first thing is a convolution. So if we look, it is looking at block of 4 by 4 pixels and calculating always like 1 pixel from it. So it's quite simple. There is nothing like mysterious going on there. It's just always looking at this small area of 4 by 4. If you notice that these lines, the color of these lines is always the same, meaning that the parameters of these lines are the same as well. Meaning this whole image, this whole thing is defined by just 16 values, 4 by 4 values, 4 by 4 weights. So this is one convolution, fine. There is another one which is different values. This is another one which is again different values. But all of these are always just 4 by 4 blocks. Good, that's simple enough. This thing is downscaling. So when we are, okay, this top left pixel, if I can find, this one pixel is calculated from the 4 other pixels because it's just downscaled. So it just will take the number of values over here, take an average, and like put it there. So I don't know. It also looks like this. It is just downsampled version of this image, like lower resolution. Fine. Here there is another convolutional layer. In this case, okay, it's again. It is now connected with more. It's connected with 4. Fine, but it's again looking at just 4 by 4 block within this image, and yeah, somehow combining it. Wow, I can zoom. I did not want to do that. Shit, how can I? Okay. Okay, good. This is a strange mouse. Okay, and this is again downscaling. Can I make it? Okay, and this layer of things, of neurons, is the fully connected neural layer, fully connected layer. So if I look at a neuron here, it has a lot of connections with everything that was in the previous layer. So you can, like, it is quite easy to see that this moment where there are these, and each one of them has different weights here, this is the moment where there is a lot of parameters suddenly in the model. Because here, okay, we have, I don't know, 4 by, like, okay, not that many, fine, not that many. Actually, this doesn't have a parameter at all because it's just downsampling. This has 4 or 16, fine. This has more, okay. This has 4 times 16, okay, but not many. Whereas this, it has a lot. Here, again, a fully connected layer. One neuron is getting inputs from all the inputs from the previous layer. And all the way here, this thing, okay, this one neuron is firing. It's a neuron called like with the, which is representing the 1. Okay, this is the class that we wanted. Okay, if I mess this up into something, let's put it is the 1. When it wakes up, okay, yep, still 1. Okay, do something like this with it. Okay, yeah, it's now it's all messed up, and it's firing on 2. If I like try to make some mess into it, it is now starting to get confused. It's thinking it's still 2, but I don't know. I think if you really mess it up, there is like, okay, this is 8, okay. But there are some moments where, oh yeah, for example, now it doesn't know, like this was not in the training set. It is thinking 0 or 2 or 9 and 8. All of them are bright lights, so it could be possible. So yeah, of course, it doesn't work on stuff that has not been trained on. So yeah, this is quite nice visualization. again, convolutions, convolutions, downsampling, another convolutions, another downsampling, fully connected, fully connected, fully connected. We are done. This is the neural network. Easy. So yeah, we are actually quite close to the end as well. When you look at the ImageNet competition, the results that we were showing before, this is the evolution of the models that they were using. So this is the LANet, you've seen that one. This is ImageNet. This is AlexNet, I mean. The naming is quite funny because this has been written by Alex Krzyzewski, and so he named his neural network. This is AlexNet, of course. Inception is, I think, by Google. VGG is, I think, by a group called VGG. No other reason for it. ResNet, at least ResNet is residual connections neural network, so there is a trick that they use with it, stuff like that. But it's quite funny to see the challenge of names that they were coming up with. So this is just the outline of what are the models. There is a lot of research going on still till today. And yeah, that's it. This is very much close to the end of the class. I would like to ask you if you are interested in attending the next one. It is possible to come the next Thursday. Well, you can come tomorrow as well, but it will be the same presentation, so probably don't come. But the next Thursday, you can come and there will be a coding example with this. So, well, today we were learning about the ideas that are being used and the mathematical theory, at least a little bit. Tomorrow, the next week, we will be looking at how to put this into code, how to look at some of the features, a model to analyze an image and give us a label. Okay, this is a cat. And just if you come, the stuff that you will need is a laptop. It doesn't have to be a powerful one because we will be working with Google Cloud, which is a cloud working server which has a lot of power, but somewhere in the cloud. So it doesn't need like you can work on any potato machine that you have, and it will be still computing the whatever you need. You can even train a model there. Yeah. So that's it. I don't know if anyone is interested. I will continue. Like if someone is interested, I would like to know some information about you in a sense of like, hey, do you know Python? Hey, have you read a scientific paper? Hey, do you work in Linux? Stuff like this.
Yeah, I think everyone can answer you that, that's so
And also there is homework, which is the less fun part maybe, but if you want, write me a mail to this mail. Maybe mark it down now, maybe if you are interested, write it to me. I will send you a link to this presentation and also to this paper. And this is from year 2012. It is a paper called by A. Krzyzewski, which is the one that is maybe this is the one that is AlexNet, basically. So this paper is quite good, and the homework is very simple. It's just read it. I will send you like the information of what parts to read because it's not necessary to read all of it. It's I think 7 pages. I have one version here. And I have a messed up version here, and the parts are some part in introduction, some part in the data set, some part all the way later in the architecture. Fine, that's important, and then ignore, and then the results. So that's what you need to read basically. I can send that as a later as the description of it. And the homework is also not really difficult. It's just I would like you to answer these 3 questions. What is the core message of the paper in 1 to 3 sentences? It can be really short and like easy. It can be a little bit more concrete if you want. So, what is the core message? What did they even do in the paper? Second is, what method did they use? What did they use for like? Okay, was it maybe it was like convolutional neural network maybe? And what results did they get? Were they nice results? Did they beat any score in that way, or is it something like okay, another random paper, not really important? There are two bonus questions which I can send this slide later to anyone who replies to my mail, so you will be able to get these. What is this strange shortcut? And then how can the model be used? okay, you John, okay, I don't understand this area at all. Fine, I will read the next one. Okay, this is actually maybe making some sense. And like later to kind of put together some idea. Yeah, I think that's how you have to start. I think, yeah. Not everyone understands what's happening in the paper, especially when you start reading them. So yeah, this is it. This is the homework. And if I can change the slide, yeah, this is it for the lesson as well. Yeah, if you're interested, there are some links to check out. The first link is for it reads almost like a story. This is an article describing which neural network architecture came after each other. So there is the story of AlexNet, GoogleNet, ResNet, etc. It is quite fun to read. It's without many descriptions of what is happening, so it's quite nice. These are the examples of the people who are working with machine learning as artists, quite non-traditional, and this is another person like this. This one, it's a good repository of tutorials and guides. If you want to start with something, this is quite good because you will be given a Python notebook which just like you take enter. It's happening. You can read it and study it in detail as well, but you can see what's happening and like it's quite easy to start with. Yeah, that's it. Finished. Yeah, some questions at the end?
Nope.
No. Good.
Todo el mundo, ¿no?
Todo lo suficientemente complicado, así que bien.
Ahí te das cuenta que uno no sabe nada.
Mm.
Sí, ¿no?
So I hope this is useful in some way. Yeah.
Pero de a poco, ahí vamos a ir agarrando el hilo.
The most part are lost.
Okay. It will become a little bit more like clear in the next class when we will be touching the code. So we actually will see, okay, this is this model, and okay, this is the image I put in it, and this is the feature that I'm getting in, and these are all the numbers. Fine, okay, it actually looks like that way. Fine, it is the correct number of numbers. Okay, fine. And then oh, this is the thing spiking here, and maybe this thing. Oh, it's a dog. Okay. So we will see that next time with code. So it may be more easier.
Yeah, sure. So I think this will be easier, you know, when you see the results or when you pour data and after that.
When you try it yourself as well.
Yeah, it's easy.
Yeah. Okay. Finished.
Finito.
The 10R, I think. Oh.